Let's now consider another example which accentuates the brute effectiveness of asymptotic expansion in comparison with Taylor one. This is an example of so-called incomplete Euler's gamma function. Here it is. We'll go through the detailed theory of the gamma function in our next lecture. Parameter z can be an arbitrary complex number in general. The integral can't be taken exactly, so we'll try to build the approximation. And we will consider two possible approximations: convergent Taylor series expansion and divergent asymptotic expansion. First, let's construct a convergent Taylor series expansion. The exponential function can be Taylor expanded for any t. We plug in the expansion into the initial expression for the incomplete gamma function. It is important to stress again that the exponential series has infinite convergent radius. Now, the integral can be rewritten in the following form. Changing the summation and integration signs, we arrive at the following sum. The initial Taylor series for the exponential converged everywhere. As a result, the obtained series is also convergent everywhere. This is a Taylor expansion for the incomplete gamma function. It converges for all finite x. It's especially suitable for small x. Indeed, let's denote the general term of our sum as an. Here is the expression for its modulus. Then you can easily see that at large n we can discard z in the denominator of an and get the following recurrence relation. So, since every other term in expansion is approximately x over n times smaller, the series is very effective for small x. But it's extremely inconvenient at larger arguments. For example, let's consider, say, x is equal to 8 and set z is equal to 5/2. The exact value of the incomplete gamma function is 1.32024. Our Taylor series does converge at this x, but at what a price? Just look at its partial sums. Here is the first term, and here are the sums of the first 2 and 3 terms. The partial sums already reached the value of 2000. The further, the worse. Here are the sums of up to 6 terms, and they reached the value of 4000. Only after this it starts to converge to its real value. So, due to its sign-changing character, the result inherits all the faults of the exponential e to minus x expansion, as you remember. To get the reasonable accuracy for x is equal to 8, we again have to sum 15 terms. Some of them are of the order of 4000. So we can't use this series for series computation at not so small x. The normal way to proceed is to construct a divergent asymptotic series. So let's do this quickly. Since we are interested in basically rather large x, we need to use the smallness of the exponential near the upper limit of the integration. But the integration range is a long segment stretching from 0 to x, where e to minus x is indeed small. To utilize the smallness of the exponential, we need somehow to exclude the region where e to minus x is large. Well, there is no universal way to do this, I'm afraid. But here there is an antidote though. The integral we discuss can be taken exactly on a semi-infinite segment, from 0 to plus infinity. At half integer z, like in our case z is equal to 5/2, it can be even expressed in elementary functions. So we represent it as a difference of the integrals on the segments from 0 to plus infinity and from x to plus infinity, like that. Indeed, here is the initial expression for gamma function, and this is the first integral. We then make a change, t is equal to s squared, dt is 2s ds, and the integral becomes as follows. It is reduced to Gauss integral by differentiation with respect to parameter technique. Well, you may argue that there is no parameter here at all, so you can't differentiate it with respect to anything. But here is a small hint. Add the factor lambda into the exponential and change it from e to minus s squared to e to minus lambda s squared. I recommend you to do this as a small exercise. If you have problems with it, look into the supplement material to this lecture. So you easily show that the integral is equal to the following expression. So it's simply 3/4 square root of pi. Now the remaining integral from x to plus infinity is estimated by integration by parts technique. It doesn't have a typical appearance of asymptotic integral, though. The integrand contains no latch parameter, which is x in our case. Moreover, the limits depend explicitly on x. To turn it into a standard form, we change the variable to Sx. Then the integral assumes a standard form with large parameter in the exponential and constant limits. Let's make two integrating steps. We turn exponential into derivative and perform the first integration, and then we repeat the step again and integrate once more. The last term is, as usual, treated as a remainder or error term. So after two integrations, we collect all the terms, and the asymptotic becomes as follows. And its value at x is equal to 8 is 1.32033. And this, for comparison, is a value after just two analytical operations. The accuracy is 0.006%. It's incredible. So this is just an example how superior a divergent series can be comparing to a convergent one. One can of course compute the full asymptotic series. Let's do it. So here is our expression after two integrations. Each integration by parts brings the exponential factor e to minus x times the accumulating product of numeric coefficients arising from the differentiation of the power of function s to 3/2, which then is turned into s to 1/2 and so on. The zero step brings 3/2. The first step brings additional 3/2 minus 1, which is 1/2. The next step is going to bring another 3/2 minus 2, which is minus 1/2 factor. So we have the following accumulating product. So the general form of the nth term in the expansion looks like this. Hence, we form the following full asymptotic series. Now we'd like to make an estimate for the error term in our series and build superasymptotics. So here is again our full asymptotic series. To write the correct expression for the error term, let's simply guess it from the step-by-step integration. So this is the result after three integration by parts. And this is the error term. We notice the accumulating factorial factor in front of the integral. We also see how power of x decays from 3/2 after the first step to 1/2 and to minus 1/2 after the third step. Simultaneously, the power of s drops one by one in the integrand of the error term. The remainder term is then as follows. Let's estimate this term in a more elaborate way. Our previous estimate of the error term was strictly speaking valid only for not very large parameter. Back then, the parameter was lambda, and we worked in the limit n is much less than lambda. However, we use it for n of the order of lambda. But, since we were interested in the order of magnitude estimate of the error, it served its purpose well enough. Of course, in principle, n can be also very large, and in many cases, we need it to be of the order of lambda. So let's see how the estimate of an error term can be built in a more accurate manner. As usual, we denote the integral in question by I of x. Let's put everything in the exponent. Actually, here we have come to the general Laplace type integral. So how do we estimate it? Well, the answer to this question is one of the main topics of our course. Here, we restrict ourselves to a more specific statement. In one of the future lectures, we will formulate a general argument that states the following. If the exponential function f of s in the integral of Laplace type is real and monotonous inside the integration segment, then the asymptotic estimate by integration by parts remains valid. So the way forward is to substitute the exponential with its entire derivative, and then integrate by parts, where the last term is obviously the remainder one. So substituting the limits, we obtain a more accurate estimate, where error r1 of lambda is defined as this. Now back to our integral. Here is our exponent function, and here is its derivative. And as a result, the integral is estimated as follows. Finally, an error function is evaluated according to the outlined scheme. So this is a more precise estimate for the error integral for our incomplete gamma function. The most important thing here is that the estimate is built with the help of our new asymptotic formula for Laplace-type integrals. Naturally, to build a superasymptotic series, we need to minimize the error function with respect to discrete n. To do so, we need to treat n as a continuous variable. At large x, there is no doubt that the critical n is going to be large as well. So we need to find the approximate expression for the factorial type product. We'll discuss this type of products in more detail in the next lecture. But I hope it's an easy exercise for you to prove that this product can be represented as the ratio of two simple factorials, like this. Now, keeping in mind that we will need large n in the end, we use Stirling formula for both of them. But before we even resort to Stirling formula, let us get rid of additional 4 and 2 in the numerator and denominator of our expression, keeping in mind that n is large. We do the following simple thing. We represent the 2n minus 4 factorial as a following ratio, and simplify it using the largeness of n. Next, we do the same thing with n minus 2 factorial. So we have a simpler version of our initial factorial coefficient in the error term. Now we employ Stirling formula for both factorials, the 2n, and then the n. And after some simple algebra, we arrive at the following expression for our error coefficient. Now we should minimize the error itself. Here is our error at large n. And as usual, we take its logarithm to make it a smooth function. And then we differentiate it over n. So here is the equation for the minimum. We can solve it by the method of consecutive approximations in the same manner as I did it before. So it's another small exercise for you. Show that the solution is simply n is equal to x plus 5 halves. Once you plug in this solution into the error term, you finally obtain the optimal error itself. Notice that the initial asymptotic series is proportional to e to minus x. But the error function is still exponentially small, as it has additional 2 factor in the exponent. So again, we achieved an exponential accuracy. We just need to truncate our series at optimal n. This, of course, is nothing but a superasymptotics. Here, square brackets mean that, as usual, the integer part of the number.